Today we're going to talk about inferences based on two samples. So essentially what we're dealing with here is we're still dealing with the idea of hypothesis tests and confidence intervals. But now we're basically going to compare two groups. We will focus on the mean. Basically in all of our comparisons, what we will be comparing is basically two means, mu1 and mu2. So there are two different ways to do this, or two common ways that your samples will look. We will either have dependent samples or independent samples. So mathematically, it's a little easier to deal with dependent samples because it's very similar to a single sample case in terms of the test statistic and how the confidence interval is calculated. So that is where we will start. So for dependent samples, what we end up with is with basically pairs of individuals in each sample. So sometimes people will be paired with themselves, like if you have a pre-test and a post-test, you will compare the individual with themselves. Basically, did their test improve? Did their score improve? Sometimes you might pair people based on just characteristics that would make them similar. The nice thing about pairing is when you pair, you reduce the variability, and reducing variability always decreases error. So sometimes if you really are worried about having a lot of error, sometimes dependent samples is better, and sometimes it just makes sense, especially in like a pre-test, post-test kind of thing where you're really testing the same person twice. So obviously you'd be paired with yourself. The point estimate, for dependent sample case, we actually call it mu sub d. We actually use this idea of differences because whenever we pair things, we can have a difference for each pair, and we actually analyze the differences for each pair, and that's really how the inferential statistics methods work whenever we have this idea of dependent samples or paired samples, as you'll sometimes hear it called. So the point estimate is mu sub d, which equals mu1 minus mu2. So mu1, of course, if it's pre-test, post-test, mu1 might be the pre-test, and mu2 might be the mean on the post-test. So you're going to define mu1 and mu2 based on your two groups. It's going to be the mean for each. And really what we look at is we look at the difference between mu1 and mu2, and that's how we define mu sub d in the paired case. The reason why we look at the difference is because the difference is really telling in terms of how mu1 and mu2 compare. Because obviously if mu1 minus mu2 equals 0, then that means mu1 and mu2 are equal. If mu1 is bigger than mu2, then that means the quantity mu1 minus mu2 will be positive, and if mu2 is bigger, that means the quantity will be negative. So we can really do a good comparison of mu1 and mu2 just based on this difference. So of course the way we estimate mu is typically by x bar. We do the same thing here. We estimate mu sub d by, we just call it d bar, which is the mean of the differences. And of course, we just use the sample means to estimate the population means. So mu sub d is mu1 minus mu2, so d bar is just x bar 1 minus x bar 2. Or really, all you have to do whenever you collect data is you just calculate the differences, and then you just take the mean of those differences, and that will give you d bar. So since we have these d values, these differences, we can actually use essentially the same test statistic as we do in a single sample case. The only difference is instead of having x bar, now we have d bar. We're just looking at the differences. But if you compare that to your old test statistic, you'll see that it's very similar. Before it was x bar minus mu over s over square root of n. Now it's just, instead of x, it's now d bar minus mu, and of course it's mu sub d over s sub d over square root of n. And of course s sub d is just the standard deviation for your differences. And n is the number of pairs. That's with n minus 1 degrees of freedom. So since we're only dealing with the differences, we still have that same degrees of freedom of n minus 1. That means that for the confidence interval is always our point estimate, which is of course d bar, plus or minus the error tolerance. And the error tolerance, if you remember before, it was t times the standard error. That's what it is here. We're dealing with t-distribution. So the standard error is just the denominator of your test statistic. So you take t times s sub d over square root of n. Okay, so let's look at an example. This is the example that we're going to look at for dependent samples, and we'll actually do both a hypothesis test and confidence intervals. Typically, of course, you would not do both on a single example or a single scenario. If you were studying something, you typically would not do both a hypothesis test and a confidence interval. You would do whatever you're interested in. But for our purposes, I want to show you the process of doing both a hypothesis test and confidence interval, so I'm going to use this single example to show you both of those. So here it says, a study was conducted to investigate if hypnotism is effective in reducing pain. So we have the data there, and I will typically give you the descriptives, so I'm not going to make you go through and calculate all the descriptive statistics for your data. But basically, we have these individuals, and we're measuring pain on these individuals using a 10-point scale. We're going to measure them twice, basically, before they are hypnotized and then after they're hypnotized. And then we want to basically see if after they're hypnotized, if their pain is lower. So you can see from the data, the first row in that table represents their pain measurement after they were hypnotized. And then the second row represents before they were hypnotized. And then, of course, we have this third row, which is the differences. And this is actually the D's. This is the information that we're actually going to end up analyzing is these differences. And you can see the way that we get those differences is we just, for each person, take the after minus the before. So like in that for that first person, you get 2.6 minus 4.6, which is negative 2.0. For the second person, you get 0.4 minus 4.5, which is negative 4.1, and so on. It is important to notice whenever you look at these kind of problems how the subtraction is working, because that will tell you which one is mu1 and which one is mu2, because we always set these up as mu1 minus mu2. So you can see from the table here that we're taking the after is mu1, and from that we're subtracting the before, which will be mu2. So it's always mu1 minus mu2, and since you can see that we're taking the after minus the before, that means that the after must be mu1 and the before must be mu2. So I already did the descriptors for you, and like I said, I'll typically do this. I'm not going to make you calculate the mean and standard deviation every time you do one of these problems. But if you calculate the mean for those differences, that's our D bar value. The mean of those differences is negative 3.475. The variance is 7.436. And of course, take the square root of that, you get standard deviation, which in this case is 2.727. Okay, so let's start out with a hypothesis test. We want to test if hypnotism was effective in reducing pain, and we're going to use alpha equals 0.01. So the first thing, we're going to use our 5 steps, the same 5 steps we always use for hypothesis testing. So we're going to start with stating our hypothesis. Then, of course, we're going to give our critical region, calculate our test statistic, then make our decision, and then interpret our results. So nothing's changed here in terms of how we do the test. Mathematically, the test statistic is, of course, a little different, but the general idea of a hypothesis test hasn't changed. So that's not new. The only thing new here is now we're comparing two means. So that's really the additional thing you have to deal with, which does add some complexity just to how to think about things and how things work a little bit, but the basic process you got to remember is always the same. Okay, so what do we want to test? So we want to test basically, does hypnotism reduce pain? So that means does their pain after hypnotism, is it less than before? So in order for it to be less than before, remember we already said mu1 is after and mu2 is before. So that means we would want to prove that mu1 is less than mu2. That means their pain after would be less than their pain before. That's what we want to prove. So we want to rewrite that. I recommend you always start with just write it as what you want to prove. We want to prove that the mean after is less than the mean before. I always start just by writing what I actually want to prove. Of course, we can manipulate this. If we subtract mu2 from both sides, we will end up with mu1 minus mu2 is less than 0. And we've already said that mu1 minus mu2 is mu sub d. So really what we're going to end up testing in terms of how we go through this hypothesis process is we're really going to be testing just a single parameter mu sub d, and we're trying to prove that that is less than 0. But do notice that proving that mu sub d is less than 0 is equivalent to proving that mu1 is less than mu2, meaning that hypnotism was effective in reducing pain. So if we're able to prove this, we're going to be able to conclude that hypnotism was effective. H0, of course, is our contradicting statement. So if HA is mu sub d is less than 0, that means H0 must be mu sub d is greater than or equal to 0. So that's our first step. We now have HA and H0. So I need some more space, so I'm going to keep the descriptives up here, but get rid of some of the details. We already have our first step done, which is our hypothesis. So now let's move to our second step. So this is a t-distribution, so we're always going to be dealing with t's when we do these two sample problems. We're not going to worry about the z. It works kind of the same way as with a single sample, where if you do know the population values, then it's a z, but it becomes a t when you estimate those with the sample. But in reality, like we talked about before, we're always going to estimate them with the sample, so we're going to focus on the t-distribution for these problems. We do have to think about our degrees of freedom. If you remember from the table, there were 8 data points in the table, or 8 individuals in the study, which means our degrees of freedom is 7. We also already determined that alpha equals 0.01. We were told to test this at alpha equals 0.01, which I also have written at the top of this slide. So based on that, we can come up with our rejection region. So when you do this, this is what your rejection region should look like. So this is a t-distribution, so draw your picture. It's not a perfect bell shape, but it's basically a bell-shaped curve with heavier tails like we talked about before with the t-distribution. So this is our t-distribution. We know we have 7 degrees of freedom because n is 8. We know alpha is 0.01, so basically it's just a matter of looking up that in the table. So you look up t of 0.01 with 7 degrees of freedom, and when you look that up, you will find that value is negative 2.998. So since we are trying to prove less than, again we look at HA. That's what we always look at to tell where the region is. That means it's the area to the left, which is why we use the negative 2.988. So we shade the area to the left because that's what HA is proving, less than. We know that area is 0.01, that's our alpha. We look that value up like I just said. You'll get 2.998 whenever you look up t of 0.01, 7 degrees of freedom. And since we're looking at less than, excuse me, that means we're looking at the area to the left here. So our rejection region is anywhere where t is less than or equal to negative 2.998. So that is step 2. Step 3. Step 3 is our test statistic. So our test statistic, of course, is a t. We've already talked about that. Our test statistic for dependent samples is going to be d bar minus mu sub d over the standard error, which is s sub d over square root of n. So really it's just plug and chug here. We plug in our values. D bar is negative 3.475. You were given that value. Mu sub d. Remember what we plug in for the parameter? It's the same as before. We're comparing mu sub d to 0. We're trying to show that it's less than 0. And basically we're assuming that it's equal to 0. Just like before what we did in a single sample. The nice thing about these kind of problems is almost always you're comparing the mean difference to 0, because you're almost always trying to prove that their values are either different or that one value is bigger than the other. So in doing that, you're pretty much always comparing these to 0, so that mu sub d quantity there is pretty much always 0 in these problems. The standard deviation of our differences is also given to us. That's 2.727. And we've already said that our sample size is 8. So it's just a matter of cranking through the math there, and you will get negative 3.604 for your test statistic. So step 4 is make your decision. So you just got to compare that test statistic and see if it's in our critical region. And of course it is. Negative 3.604 is inside of that shaded region. It is less than or equal to negative 2.998. Negative 3.64 is in the shaded region in our picture. So that means we reject H0. So I hope you see that these steps are exactly what we did before. It's really just using the new formulas and dealing with the fact that we have two samples. That means we can make our conclusion. And since we're able to reject H naught and say it's false, that means we can conclude that HA is true. And that means we can conclude that hypnotism is effective in reducing pain based on our measurements here. So that's how you do a hypothesis test for dependent samples. So let's do a confidence interval. So we're just going to use the same data. So I just kept the same data up here. We're going to construct and interpret. In this case, we're going to do a 90% confidence interval. So remember, with a 90% confidence interval, confidence intervals are always two-tailed. So that means alpha in this case is 10%. So that means we divide that 10% in half and we get 5% in each tail, because there's always a probability that it's below the interval and there's always a probability that it's above the interval. So each of those in the tails are 5%. So that means our t-value here is going to be t of 0.05. We have 7 degrees of freedom in -1. So that will give us, when you look this up in the table, 1.895. So we need that in order to calculate our error tolerance. So I went ahead and looked up that value. And then once you look up that value, it's pretty straightforward. You just do what you always do. We already know the statistic d bar, so that means we need our error tolerance. So our error tolerance here is t times standard error, S sub d over square root of n. We just figured out t to be 1.895. Everything else we're given. S sub d is 2.727, and remember the sample size was 8. That will give us an error tolerance of 2.110. Then we take our statistic, d bar, and we just add and subtract e. So like always. So d bar here is negative 3.475. We just figured out e. So we add and subtract e, which is 2.110. That will give us our interval. So our interval here works out to be negative 5.585 to negative 1.365. So since both of these values are negative, what that tells you is the way you get a negative when you look at mu1 minus mu2 is you get negative whenever mu1 is less than mu2. When you take a number and you subtract a bigger number, that's when you get a negative. So since both of these values in our confidence interval are negative, that means mu1 here must be less than mu2, which is what we've already concluded anyway for this scenario. So since mu1 must be less, that means that after hypnotism, the mean must have been less. And this tells us by how much. So this means that we are 90% confident that hypnotism reduced pain by between 1.365 and 5.585. So in your interpretation here, even though these quantities are negative, it really makes sense to change those into positive and just talk about how it reduced pain, because the reduction is why you get the negative. It reduced pain, so we get a negative. But whenever we interpret that, we can just simply say we reduced pain by between 1.365 and 5.585 in terms of this pain scale that we used in this scenario. And that's a confidence interval for dependent samples. So the nice thing about dependent samples is, since you have these pairs and you create this list of differences, really you're only dealing with just the differences. So it's almost like just dealing with a single variable. It just changes your interpretation and how you have to set up your hypothesis. But for the most part, it's exactly the same as what we did before. Independent samples is a little more messy because with independent samples you can't pair, because with independent samples, of course, by definition, independent samples mean one sample is not related to the other sample. So you don't have any kind of pairing where you can subtract and create differences for each pair. Instead, you basically just have two groups that you have data sets for. The point estimate is still the same, other than now we don't write anything as mu sub d, because we no longer have these differences for each individual. So we no longer have this single variable. So whenever you deal with independent samples, you really do have to deal with kind of the two means separately. So we just end up with a point estimate. It's very similar. It's mu1 minus mu2, but we don't end up being able to combine them because we don't have this single column of differences that we can calculate because we just have these two separate samples. So our point estimate ends up being mu1 minus mu2, and of course we estimate that by x bar 1 minus x bar 2. We are going to focus on the scenario where our variance is equal across the two groups. You can also calculate and compute hypothesis test and confidence intervals when you have unequal variances, but it is a little more messy, and it's something that we're not going to do for our purposes. We're going to focus on scenarios where we're going to assume that the variances are equal. So since we're assuming that mu1 and mu2 is equal, we have to be able to calculate a value to represent the variance for these two samples. So we call this the pooled variance, and you can see the formula there. We call it S sub p squared. P stands for the pooled, basically pooled. It's a pooled variance. So it's our estimated variance for both sample 1 and sample 2. So it estimates both sigma squared 1 and sigma squared 2, the variance for each of the samples. The way we calculate this pooled variance is we just basically weight it based on the degrees of freedom. The degrees of freedom here is actually going to be the denominator that you see in the pooled variance, which is n1 plus n2 minus 2. So we're used to, with degrees of freedom, always subtracting 1, and that's because we've always dealt with one data set. But in independent samples, we actually have two different data sets to deal with, which is why you end up subtracting 2. It's basically a combination of the degrees of freedom for each data set. So we basically have n1 minus 1, which you can see on the top, and n2 minus 1. Whenever you combine n1 minus 1 plus n2 minus 1, you end up with that denominator, which is n1 plus n2 minus 2. So basically, that's just a weighted average of the variances for the two samples. That's how we get our pooled variance. Once you get that pooled variance, then you can calculate your test statistic. This test statistic's in the same form as all the others that we've dealt with, but it does look a little more messy. We take our observation, which is x bar 1 minus x bar 2. That's the first thing you see in there, in that test statistic T. From that, we subtract the parameter, which is mu1 minus mu2, and then we divide by the standard error. And the standard error is a little messy here because we have two different samples. So instead of just having one fraction, you end up with 2. It's basically the variance over n. Take the square root of that. That's what it looked like before, but now we have 2 of them. So you end up with a standard error that looks like this, the square root of this quantity, where you get s sub p squared over n minus 1 plus s sub p squared over n minus 2. And as I've already mentioned, the degrees of freedom here is n1 plus n2 minus 2. This means for a confidence interval, we take our point estimate. Our point estimate here is x bar 1 minus x bar 2, and we add and subtract e. And then from that, in order to get e, we just take t times the standard error. The standard error is always the denominator of our test statistic. So as you can see, it's that square root that comes from the denominator of our test statistic. And that's basically the process. So the process is going to be the same here. But the formulas are messier in the independent case. The formulas are kind of messy. So I wouldn't say it's hard, but it is tedious, because if you make a simple mistake, then obviously you mess the whole thing up. So you got to be careful. It is kind of tedious to do these problems because the formulas are kind of messy. Not super difficult, but just messy. So let's look at an example here. And we'll do the same thing here. We'll do both a hypothesis test and a confidence interval. So here's our scenario. The average time boys and girls spend playing video games each week is believed to be different. So that's what we're going to test. We're going to try to show that boys and girls play video games a different amount of time each week. We're going to assume, like I said we would, that the variances are equal. We're going to assume sigma 1 squared equals sigma 2 squared. So here's our data, along with the descriptors. So I would give you all this information. I'm not going to make you calculate all the information. But you can actually see here that the sample sizes are different. So there is a sample size for the boys, which is 7, and a sample size for the girls, which is 6. So the sample sizes don't have to be equal when you have independent samples, because the samples are independent. Lots of times they will be equal, but they don't have to be. Like in the dependent case, since you have the samples paired, the sample sizes, there is really just one sample size because you have the same number of people in each group and you're creating this list of differences. So here we have two totally separate samples. These samples are independent. And then we need the descriptors for each one, and you can see for boys the sample size is 7. The sample mean is 6.371. The variance is 6.486, and the standard deviation is 2.547. For girls, the sample size is 6. Mean is 6.867. Variance is 5.375, and the standard deviation is 2.318. You can also notice that for boys, we're calling boys is going to be represented by mu1. Girls are going to be represented by mu2, and you can see that based on the notation from those tables. That's why we have all the boys' stuff subscripted with a 1, and the girls' descriptives subscripted with a 2. Okay, so we want to test this belief, the belief that the amount of time they spend playing video games is different. We want to test that, and we're going to use alpha equals 0.05. So, step 1, what do we want to prove? Well, we basically want to prove that the mean for the boys, mu1, is different than the mean for the girls. So we just want to prove that these two means are not equal. We can rewrite this, and this is how we always want to do it. We want to rewrite it in such a way that we end up with mu1 minus mu2. So you just subtract mu2 from both sides of that inequality, and you get mu1 minus mu2 is not equal to 0. That is HA. That's what we want to prove. So notice with independent samples, there is no mu sub d. We're just going to leave it as mu1 minus mu2 because we don't have this set of differences that we can analyze. So that means H naught just contradicts that. H naught contradicts that. So if HA is mu1 minus mu2 does not equal 0, H naught should be mu1 minus mu2 is equal to 0. So that is actually a typo. So that should say equal to 0. Okay, to give ourselves some more space, let's move over here. So step 2. Step 2 is our rejection region. So we're testing not equal to. That means we have area in both tails. So since we have area in both tails, that means we divide our alpha level in half. So alpha is 0.05, which means we put 0.025 in each tail. We know we have, we have 7 for the boys of a sample size and 6 for the girls. Remember, we take N1 plus N2 minus 2. So we take 7 plus 6, which is 13, minus 2, that gives us an 11. So we have 11 degrees of freedom here. So you got to remember how to do that. We take N1 plus N2 minus 2. So here we take 7 plus 6 minus 2, which gives us 11. We have 11 degrees of freedom. So we look up T of 0.025, 11 degrees of freedom. You will get 2.201. So since this is a two-tailed test, that means we're going to reject the null hypothesis H naught if our t value is less than or equal to negative 2.201, or if our t value is greater than or equal to 2.201. To calculate our test statistic, we have to start with this idea of a pooled variance. So this is just that pooled variance formula. So you can see I really just plugged in the information that we're given. The pooled variance here, we're going to take N1 minus 1, so that's going to be 7 minus 1, times S1 squared. S1 squared is 6.486. And to that, we're going to add N2 minus 1, which is 6 minus 1, times the variance for the girls, which is 5.375. That's divided by the standard deviation, which is 7 plus 6 minus 2. That's divided by not the standard deviation, by the degrees of freedom, which is 7 plus 6 minus 2. And if you crank through the math there, you'll get a pooled variance here of 5.981. The pooled variance will always have to be between the two variances. So if it's not, you know you made a mistake. So you can see S1 squared is 6.486. S2 squared is 5.375. You get a pooled variance of 5.981, which is in between there. So it'll always be in between there. If it's not, you made a mistake. If you have the same sample size, you can actually just average those two variances. But since we don't have the same sample size here, it's not an exact average. It's a weighted average. Now that we have that pooled variance, we can calculate our test statistic. So our test statistic here, x bar 1 minus x bar 2, we just plug in and we get 6.371 minus 6.867. So that really is our point estimate. From that, we are going to subtract the parameter, mu1 minus mu2. So keep in mind, I've already mentioned this with dependent case, true with independent case as well. When we're comparing samples, we're pretty much always comparing to 0. So that mu1 minus mu2 will pretty much always be 0. If you look up at what we're testing, you can see we're comparing it to 0, so that quantity is going to be 0. And then the denominator for the pooled variance, we just plug in what we calculated that to be, which is 5.981. For N1, we plug in 7, and for N2, we should plug in 6. So to give ourselves some more room, I'm going to move over here. But now we have our rejection region. We now also have our test statistic. So now we can make our decision. So to make our decision, we're going to see if our test statistic is within our rejection region. So we're looking to see if negative 0.365, that's our test statistic. We're looking to see if it's in our shaded region or our rejection region in step 2. And we can see that it is not. Negative 3.65 is not less than or equal to negative 2.201, and it is not greater than or equal to 2.201. So therefore, here we have to fail to reject H0. So since we fail to reject H0, that means there is not sufficient evidence here to prove there's a difference. So our final part of this hypothesis test is just our conclusion. So we should say something like this. We should say something to the effect that there is not sufficient evidence to conclude that the average time boys and girls spend playing video games is different. So something like that. Okay, now that we've done a hypothesis test, now let's do a confidence interval. So we're going to use the same scenario. We're going to construct a 95% confidence interval. Some of the work we've already done here, so since we used alpha equals 0.05 for the hypothesis test, and since we're tested not equal to, that means it's a two-tailed test. So this is also a two-tailed test. So that means we have 2.5% of error in each tail because it's confidence intervals, which are always two-tailed. We have the same degrees of freedom, which is 11. So we actually end up with the same t-value here of 2.201. We also have already calculated the pooled variance, so there is no need for us to do that again. We've already calculated that pooled variance, so I just moved it over here as well. It's the exact same process. You need the pooled variance in order to do a confidence interval, but we already calculated it to be 5.981, so we're just going to use that quantity. So now, we already have our statistics because we have x bar 1 and x bar 2, so we can calculate our error tolerance. So our error tolerance is just t times the standard error, so we really just plug in. For t, we plug in that 2.201. We plug in our pooled variance of 5.981, plug in our sample sizes of 7 and 6. That will give us an error tolerance of 2.995. Once we get that, we can take our statistic, x bar 1 minus x bar 2, and add and subtract that error tolerance. So of course x bar 1 minus x bar 2 we just plug in, which is 6.371 minus 6.867. That will give us negative 0.496. From that we're going to subtract and add our error tolerance, which is 2.995. That will give us our interval. So our interval here is negative 3.491 to 2.499. So now we need to interpret. So notice here we have both a negative and a positive, and the interval includes 0, which means we're not going to be able to conclude that this is not equal to 0. And we kind of already said that in our hypothesis test. We said that we can't conclude who played video games more on average, and that's why 0 is included in this interval, because the data here does not make it clear as to which group played video games more. So that's why you see 0 in the interval. So the negative we know, the fact that it's got a negative and a positive, the negative The way we would get a negative, since boys were mu1 and girls were mu2, if we take mu1 minus mu2 and we get a negative, that means mu2 must be bigger. Mu1 minus mu2 to get a positive means that mu1 must be bigger. So the negative here means that's how much at most the girls could have played video games more since they were mu2. And the positive is how much more boys could have played video games since they were mu1. So interpretation, I'm going to move things around a little bit here so that we have enough room. I basically just got rid of the descriptors at the top. But to write our concluding statement, it's going to be something like this. You want to say something to the effect that it is unclear who spent more time playing video games. It is unclear if boys or girls spent more time on average playing video games. If boys did spend more time, since they were mu1, it was by at most 2.499 hours, because mu1 minus mu2 to be positive means mu1 is bigger and mu1 was the boys. If girls spend more time playing video games, it is by at most 3.491, and the reason why we know that is because mu1 minus mu2 to be negative means mu2 must have been bigger. So since girls were sample 2, that means that the negative represents the most girls could have played video games more than boys. And of course here, really at the end of the day, we can't conclude who played more, but the confidence interval does give us a little more information. It says by at most how much each group could have played more with 95% confidence. So the interpretations here are a little trickier, and with the independent samples, the math is messy, but I hope you see that it's the same process. Focus on the process. You'll have to get the details down of these formulas and the interpretations and how we deal with having two samples down, but that's really the new part. The overall process is the same. So the focus in this section is really being able to do confidence intervals and hypothesis tests when you're comparing two means. That's really the focus here. And that's it. That's what we do in this section. That is the end of section 11.